conditions. Now I will explain boundary conditions of this Cohen equation. Now boundary condition 1 is at r is equals to 0 at center of a sphere QR cannot be infinite. So C1 must have to be equals to 0. Therefore C1 equals to 0. We can see here in the equation QRF is equals to Sn naught into r by 3 plus b by 5 r cube upon r2y plus C1 by r square. If we substitute r is equals to 0, QRF will not be defined. So therefore C1 is equals to 0. Therefore, QRF is equals to Sn naught into R by 3 plus B by 5 into RQ upon R2y. This will be QRF. Similarly, QRC we can calculate by the equation d of dr of R square QRC equals to 0. So QRC will be equals to C2 upon R square. Now we will calculate C1 C2 by boundary condition 2. At R is equals to RF, QRF is equals to QRC. Okay, now, so we will get C2 as Sn naught into 1 by 3 plus B by 5 RF. Now we will calculate C2 by R square is equals to Sn naught into R by 3 plus B by 5 R cube upon R2. After rearranging C2, we will get the value of C2 as this. And here also R is equals to R. Here we will substitute RF is equals to R. So the final equation of C2 will come as C2 is equals to Sn naught into 1 by 3 plus V by 5 RF whole cube, which will be common among these two terms. Now we can see KRC is equals to C2 upon R square. We will substitute the condition QRF is equals to QRC. Now QRC is equals to Sn naught into 1 by 3 plus B by 5 R cube upon R square. Here we substitute a C2 here and R square comes here. Now QRF will equals to Sn naught into R by 3 plus B by 5 R cube upon RF whole square. Now we will find out QRC as Sn naught into 1 by 3 plus B by 5 RF cube upon R square. Here QRF and QRC both are known. So this will be our equation number 1 and equation number 2. By using equation 1 and 2, we can calculate temperature profile by using Fourier law of heat conduction. We will substitute QRF is equals to minus KF dTF upon dr, which will be equals to Sn naught into R by 3 plus B by 5 R cube upon R2. Now we will just rearrange the term. We will divide both sides by k and we will get as dtf upon dr equals to minus Sn naught upon k into r by 3 plus b by 5 r cube upon r2. We will just integrate this equation and we will separate the terms dtf and dr by cross multiplying each other and integrating both sides. We will get the tf term. A tf will be equals to minus Sn naught upon k into r square upon 6 plus b by 5 r के power 4 upon rf square into 4 plus c3. So the final equation will be here as cf is equals to minus Sn naught by k into r square by 6 plus b upon r2f into r to power 4 upon 20 plus c3. To calculate c3, we will use another boundary condition. At r is equals to rf, tf is equals to tc. Putting this in equation 1, we will get Tc is equals to minus Sn naught upon Kf into Rf square upon 6 plus B upon Rf square plus into R 4f upon 20 plus C3. So we will substitute the boundary condition here. Tf is equals to Tc and we will calculate and we will find out Ct and we will C3 and we will resubstitute in equation this and to find out the final equation of Tc. So similarly, you can see here we have just substituted the boundary condition and we calculated C3 here. And putting the value of C3 in above equation, we will get TF as minus Sn naught upon Kf into R square by 6 plus B by Rf2 into R power 4 upon 20 plus Tc plus Sn naught upon Kf into 1 by 6 plus B by 20 into R square. This whole equation we will just transfer Tc on the left hand side and we'll get temperature profile as Tf minus Tc is equals to this term into Rf square plus this term minus this term. Similarly, from equation 2, you can see equation 2 here as QRC is equals to Sn naught into 1 by 3 plus B by 5 R cube upon R square. We will just use Fourier's law here and we'll substitute KRC as minus K dt dtc upon dr. Now you can see here we have substituted QRC as Fourier's law of heat by using Fourier's law of heat conduction, and which is equals to Sn naught into 1 by 3 plus b by 5 Rf cube upon R square. Now just we will rearrange the terms and divide both sides by minus Kc, and we will get this term. Now we have will separate Tc and Tr terms both sides, and we will integrate to get Tc. Now Tc will be Tc is equals to minus Sn naught upon Kc into 1 by 3 plus b by 5 Rf cube into minus 1 by R plus C4. Basically, we will integrate and get this equation. 1 by R square integration is basically minus 1 by R, which is just shown here. Then we will calculate Tc, and to calculate C4 term, which is here, we will use another boundary condition, which will be boundary condition 4 now. At R is equals to Rc, we will have the same temperature profile. Tc is equals to T naught. By putting this in above equation, we will calculate T naught, and we will resubstitute C4 term in this equation to get final equation. So putting value of C4, we get this is equals to Sn naught upon Kc into 1 by 3 plus b by 5 Rf cube upon R plus T naught minus Sn naught upon Kc into 1 by 3 plus b by 5 R cube upon Rc. So we will calculate Tc minus T naught will be it will be equals to Sn naught upon Kc into 1 by R plus 1 by Rc into Rf into 1 by 3 plus b by 5. This is the temperature profile for the second case, and these two are the required conditions for our question. We have solved everything, and we have discussed each and every temperature profile. Also, we have shown each and every step in detail of by integrating and substituting every value.
Our next question is, consider a long cylindrical nuclear fuel rod surrounded by an annular layer of aluminum cladding. Within the fuel rod, heat is produced by nuclear fission. This heat source depends on position approximately as Sn equals to Sn naught 1 plus B into R square by capital R square, where Sn naught and B are known constants and R is radial coordinate measured from axis of cylindrical fuel rod. In this question, we have to calculate maximum temperature in the fuel rod if outer surface of cladding is in contact with the liquid coolant, which is at a temperature TL. Heat transfer coefficient at cladding coolant interface is HL, and thermal conductivities of fuel rod and cladding are KL and KC respectively. So if we look at diagram, so this is fuel, fuel element, radius RF, and this is coolant of radius RC, and this cladding is made up of aluminum, and here outside the cladding this is coolant. So going forward for solution, so we have chosen coordinate system as spherical. So as we know, there are three coordinates in spherical system, three directions in spherical coordinate system. One is r, theta, and z. If we talk about theta direction, so our problem is symmetrical in theta direction. So temperature will not change in theta. So T is not a function of theta. We talk about Z. So if end effects are neglected, so then temperature will not vary in Z direction. So T is not a function of Z, and T will vary only in R as heat is generated inside the fission nucleus. So that heat will be conducted outwards in radial direction. Then if we look on overall energy, shell energy balance, then a rate of energy in by convective transport minus rate of energy out by convective transport plus rate of energy in by molecular transport plus rate of energy out by molecular transport plus rate of work done on system by molecular transport minus rate of work done by system on molecular transport plus rate of work done on system by external forces plus rate of energy production. This all comes to zero. So if we look on the first one, that is rate of energy in by convective transport. Since there is no bulk motion of particles, so conductive transport is not here in this case. So rate of energy in by conductive transport will be zero, and same reason for second term also. This is also zero. If we talk about third term, rate of energy in by molecular transport, so it will be a non-zero term since the heat which is transferred from nuclear fuel to the aluminum cladding is done by molecular transport. So this third term and this fourth term, these both terms are non-zero. And the next one, rate of work done on system by molecular transport. Since there is no convective transport, because there is no bulk motion of fluid, so this term becomes zero. This term also becomes zero. Now, next, rate of work done on system by all external forces. Since we are not applying any additional force or some extra force on system, so this term also becomes zero. Last one, rate of energy production. Since there is a nuclear fusion reaction occurring, so energy is generated continuously. So this last term is unknown to them. So after all non-zero and zero terms, we are left with only three terms that are rate of energy in by molecular transport minus rate of energy out by molecular transport plus rate of energy production. And this all terms comes to zero. So for applying energy shell balance will rate, but we only have flux, energy flux. So if we multiply energy flux by corresponding area, we can get rate of energy at that particular location. So if we multiply flux by area, that is QR multiplied by 2 pi RL at R plus delta R minus QR into 2 pi RL at R equals to Sm multiplied by 2 pi RL multiplied by delta R. We have multiplied by minus 1 in the shell energy balance equation, then we have arranged, we got this equation. Now we will divide by 2 pi RL, and after using the definition of first differential, we get del by del R of R to R equals to Sm, and we know Sm equals to Sm naught 1 plus B R square by R square. And from Fourier's law of heat conduction, we know QR equals to minus K dt by dr. We have calculated dTf by dr equals to minus Sn naught R divided by twice Kf all multiplied by 1 plus B R square divided by twice of capital R square plus C1 by R, where C1 is constant of integration. Same thing we have done for cladding, that is d by dr of Tc equals to C3 by R. See, C3 is integration constant. If we integrate equation 4, we get equation 4a. Now, to solve or to get the values of all these constants, we need boundary conditions. So, our first boundary condition is that at r equals to 0, Tf is defined. Tf has some value at r equals to 0. So it cannot be undefined. So this is known as positive boundary condition. Boundary condition 2. At r equals to r, Tc equals to Tf. And this boundary condition is known as empirical continuity. And if we talk about boundary condition 3, which is at r equals to r, we have flux continuous or flux continuity, which is QRF is equal to QRC. And if we talk about boundary condition 4, then we have at R equals to RC, we have conservation of energy, law of conservation of energy. That is, amount of heat conducted will be equal to amount of heat convected. So, at capital RC, we have QRC equals to HL into delta T. Delta T is our EC minus QA, and this law is known as Newton's law of Coulomb, which is the main governing law in case of convective heat transfer or convective transport. So, first we will start from question number 3. We have written question number 3 as it is, as we have derived earlier. Now, from here, we wish to get the temperature profile of fuel element. So, we have multiplied by dr both sides, then we have integrated. So this becomes integration of dTF equals to this whole term integrated with respect to dr, since S and naught divided by twice kf. This term is independent of r, so it can be taken out the integral sign. So this integration of dTF becomes df equals to, we have taken out minus Sn naught by twice of kf. Then we have integrated the remaining terms with respect to r. So that r becomes r square by 2. So we have already 2 in denominator and we have got r square by 2. So that 2 into 2 becomes 4. So we got minus Sn naught r square divided by 4k. And similarly, we have integrated other terms with respect to r, and we have got this Sn naught r square divided by 4 times of kf, or multiplied by 1 plus br raised to power 4 divided by 4 times r square. Plus, now integration of 1 upon r is ln r. We have got C1 ln r plus C2, which is constant of integration. Now, let's say this equation number 5. Now, by using flux continuity condition, we can calculate Cp very easily. Like at capital Rf, we have flux continuous, that is QRF will be equal to QRC. And from Paul's law of conduction, if we substitute the value of Q by minus K dt by dr for both fusel and cladding. So from that, we can easily get the value of Cp, which comes out to be Sn of r square divided by pi square multiplied by 1 plus b by 2. Now, we can get the value of constant C4 by using boundary condition 4, which is law of conservation of energy. So at capital RC, we have QRC equals to HL into EC minus T. So we can get value of constant C4 from equation number 4a. You can see here equation number 4a, which is EC equals to C3 multiplied by ln R plus C4. So we can easily get the value of C4, which comes out to be TL minus KC divided by RCHL. plus ln RC multiplied by C3. And we have calculated the value of C3 just in previous step. So we substituted C3 value here. So we got now C4. This C4. Now we need to calculate C2 to get the temperature profile. So we can calculate constant C2 using boundary condition 2, which is at R equals to capital RF, temperature is continuous, which means at capital RF, TF is equals to TC. So C2 comes out to be this. TF is Sn naught RF square divided by 4 times KF whole multiplied by 1 plus b by 4 plus Sn naught RF square multiplied by divided by twice Kc multiplied by 1 plus b by 2 whole multiplied by ln of Rc divided by Rf plus Kc divided by RCHF. So now we have calculated C1 and C2 both. So now we can easily calculate the value of TF by putting it in equation number 5, which is this. So after putting C1 and C2 equation 5 and rearranging all terms, we got our final expression as Tf max minus Tf equals to Sn naught multiplied by capital RF square divided by 4 times of Kf whole multiplied by 1 plus d by 4 plus Sn naught capital RF square divided by twice Kc multiplied by 1 plus d by 2 whole multiplied by Kc divided by Rc into HL plus ln of Rc by half.